Hello everyone and welcome to my presentation. First of all, let me thank you all for coming here today. As you can see on the screen, our presentation topic today is Extreme Gradient Boosting Regressor and Shapley Additive Explanation for Crop Yield Prediction in Agriculture. Before I continue my presentation, I'd like to quickly introduce myself. I am Mariadass, the first author of this paper, followed by Ervin Gubin Moung, Maisarah Sufian, and Ali Farzamnia. This presentation is structured as follows, whereby it starts with introduction, followed by motivation, objective, methodology, flowchart, selection of machine learning model and performance evaluation, visualizing future importance, and finally conclusion and future works. Agriculture is one of the most important societal concerns since it produces a large amount of food. However, despite growing populations, many countries are still hungry due to food shortages. To increase the nation's food security, policymakers must rely on accurate crop yield predictions in order to easily obtain trade-related evaluations. Machine learning can help anticipate yields more accurately. This paper proposes the XGBoost, an adaptable machine learning framework for tree boosting for crop yield prediction in Malaysia. The proposed model makes prediction based on historical data with various attributes related to Malaysia's climate fluctuations and pesticide usage in recent years. Furthermore, the performance of a predictive model is determined by how the model establishes patterns and relationships among attributes in the dataset. Apart from industrialization, which fueled Malaysia's significant economy and development, the country's agriculture industry performs a major role in guaranteeing food security and safety, as well as long-term development and wealth creation. Machine learning can assist in more precise yield prediction. As a result, a reliable crop yield prediction model is necessary for the nation's policymakers to obtain effective trade and import evaluations that will increase national food security. A precise crop yield prediction model can also assist farmers in making decisions about what to plant and when to seed it. The objective of this paper is to develop a regressor-based crop yield prediction system and to investigate the important attributes that influence crop yield using the Shapley Additive explanation, or also known as SHAP. There are 5 stages in this paper. Methodology, whereby in stage 1 is dataset formation and description, followed by data preprocessing, selection of machine learning technique, evaluation of machine learning algorithm performance, and finally visualizing feature importance. As shown on the screen, this is the flowchart of the experiment in this paper. Further explanations of the flowchart will be explained. During dataset preparation, data for crop yield and pesticides were collected from Food and Agriculture Organization of the United Nations. Data for rainfall and temperature were collected from World Bank Open Data. All these data are merged to form the dataset. The reason on why these data are collected is that there is no latest data about crop yield with the future that can influence it from Malaysia. The latest data ranges from 1990 to 2019. Next is the description of the attributes from the dataset. There are 7 attributes in the dataset, consist of area, item, year, average temperature, average rainfall, pesticide, and yield. The dependent variable is the yield attribute, meanwhile the independent variable are average temperature, average rainfall, and pesticides. The attributes area, item, and year are removed later during modeling because these attributes does not have any effect on it. During data preprocessing, there are 4 stages which consist of identifying missing values, outliers, one-hot encoding method, and feature scaling. Outliers are extreme value present or the values that do not follow the patterns in the data. One-hot encoding method is a process by which categorical variables are converted into a form that could be provided to ML algorithms to do a better job in prediction. This creates a binary column for each category and returns a sparse matrix or dense array. Feature scaling is a step of data preprocessing that is applied to independent variables or features of data. It basically helps to normalize the data within the particular range of our dataset on the same scale. The above table shows the subset of the original dataset, and the below table is the subset of the dataset after data preprocessing. Next is the selection of machine learning model and the performance evaluation. XGBoost have been used for the development of the regressor-based crop yield prediction system. R-square, mean absolute error, mean square error, and root mean square error have been used to evaluate the performance of the model in crop yield prediction. R-square is a metric that tells us the proportion of the variance in the response variable of a regression model that can be explained by the predictor variables. This value ranges from 0 to 1. The higher the R-square value, the better a model fits a dataset. Next is the mean absolute error. It represents the average of the absolute difference between the actual and predicted values in the dataset, or also known as residuals. A residual is a measure of how far away a point is vertically from the regression line. Simply, it is the error between a predicted value and the observed actual value. Mean square error represents the average of the squared difference between the original and predicted values in the dataset. It measures the variance of the residuals. Root mean square error is the square root of mean square error. It measures the standard deviation of residuals. Both the mean absolute error and root mean square error can range from 0 to infinity. They are negatively oriented scores, therefore lower values are better. In the experiment part of the paper, XGB regressor and decision tree regressor have been used with the same dataset. From the results obtained, XGB regressor shows better results compared to decision tree regressor. XGB regressor and decision tree regressor has an R-squared value of 0.98 and 0.97 respectively. Since mean absolute error and root mean square error can range from 0 to infinity, lower values are better. And when compared with XGB and decision tree regressor, XGB has the lower value in mean absolute error and root mean square error. To further explain the importance of each feature, the shape bar plot is created. By default, the shape bar plot will take the mean absolute value of each feature over all the rows of the dataset. The importance of each feature is shown better with the mean shape values of average temperature, average rainfall, and pesticide. To identify how far is the feature importance between each other is the reason bar plot is created. By this way, we can quantify the difference between the feature importance. The shape bar plot visualized by XGB regressor shows that average temperature has a higher feature importance, followed by average rainfall and pesticide. Meanwhile, the shape bar plot visualized by decision tree regressor shows that average temperature has still the higher feature importance, followed by pesticide and average rainfall. Our proposed regression model, XGBoost, also shows comparable performance to decision tree and the hybrid MLR ANN with 0.98, 0.99, and 0.99 respectively, and outperform all the other models in the R-squared metric. As in for the root mean square error and mean absolute error, Both the RMSE and MAE are negatively oriented scores, whereby lower values are better, but the range of the values of all the other authors differs, thus making it hard to compare the values. In this research work, the XGBoost regression model was suggested to predict crop yield in Malaysia. The dataset used in this study was generated by combining different publicly available datasets, which consist of important attributes such as average rainfall and average temperature and pesticide. By visualizing the output of the proposed model using SHAPE, it was discovered that the average temperature is the most important independent attribute in predicting crop yield, followed by the average rainfall and the amount of pesticide used. Assessment based on the performance metrics proved that the XGBoost model is a powerful tool for crop yield prediction tasks. For future research, we aim to develop a universal regression model that can predict crop yield across different countries. Although it might be a great challenge due to the difference in so many aspects like weather and climate fluctuations, integrating datasets related yield prediction from different country origins could be a good starter to make the development of a universal regression model possible. The parameters such as pesticide, average rainfall, and average temperature will be adjusted to identify the performance of the model in different conditions. That is all from me. If you have any questions, feel free to ask. Thank you.